Hello and welcome to the 181 video on probabilistic linear regression. So today we'll be taking another look at linear regression techniques, but sort of from a different perspective. So when we were talking about linear regression, we sort of gave you a loss and we gave you a process for going about finding the optimal W, but you might have had some questions like, how do we choose that loss function? Why do we know that our assumptions make sense? Or like, is there some other sort of statistical foundation for regression? Like, what are some other ways that we can know it's sort of true? And that's what we're going to be looking at today. We're going to be approaching it from a different perspective. We're going to be doing maximum likelihood estimation and maximum a posteriori estimation to give you two other ways that we can actually get the same results that we got in linear regression, to give you a little bit more confidence in it, or also give you a different way to think about what the math means intuitively. So specifically, we're going to create a generative process for our data. And a generative process is sort of like, in Stat 110, we have stories for distributions, and a generative process is sort of like the story for our data, like how did we get it? And then we're going to use that generative process, we're going to assume that's true, and we're going to use it to find the best sort of coefficients. And we'll see that we get the same results as linear regression. So first, assume that we have some data x and y, and our generative process is for each xn, so for each data point, our data point yn we assume comes from a normal distribution centered on wtxn with standard deviation beta to -1. So basically we're assuming that for some xn, if you have the true w, then y is a random variable, and it's going to come from a normal distribution with mean, like the dot product of w and xn, but there's some sort of like distorting noise in beta. So it isn't always, even if you had the perfect w, you wouldn't always get yn because there's some sort of noise injected into the system. And so now this first technique that we're going to do is called maximum likelihood estimation. So basically, we have some likelihood function, right? Which is like, we get our x, we get our y, we get our beta, but we choose some w. And based on that w that we choose, that changes that factors into sort of the generative process. And we assume that based on that w, that's how y was generated. So it changes how likely we think we are to see that data. So basically, the likelihood function says if this is the true w, how likely would we be to get these results, these data? And we want to choose the w that maximizes that, right? Because we want a w where we're pretty confident, like, oh, it's pretty likely that we would have gotten these results. We'd much rather have a w where there's like a 90% chance that you would have gotten this data than a 1% chance that you would have gotten this data. So our likelihood function is just, we assume all the data points are independent, so it's just the product over all the data points of, and this is a little bit of an abusive notation here, but of like the probability that yn equals that yn has its value. So that's just based on the normal distribution, right? Because yn is distributed normally. So again, as I said earlier, we want to maximize this. So maximizing this is the same thing as maximizing any monotonic transformation of this. So we can take the log of both sides because the log is a monotonic transformation. And so anytime you have like a large product and you are going to maximize something later, so you're probably going to end up taking some derivatives, you definitely don't want to be have a super large product, so you can turn that into a sum by using a log. So here on the right hand side, we just use log rules, right? The log of the product is the sum of the logs, and then I also just use the equation for the normal PDF. And then we can go ahead and use log rules, so we split it up like this. Now, an important realization here is we're just trying to maximize this over w, right? So we don't care about terms with no w dependence. In other words, this first term right here, if we just take another monotonic transformation and we just subtract this value, and we maximize that over w, that's the same thing as maximizing the log of the likelihood over w, because this doesn't change with different w terms.
And side note, this should actually be the sum from n equals 1 to big N of log of 1 over square root 2 pi b to the negative 1, but regardless, it's not dependent on w, so we can still get rid of it.
So that's exactly what we're going to do. We're going to find the w that maximizes this. And then, actually, to make it look a little bit more like linear regression, we're just going to divide everything by beta. Note here, importantly, that beta is positive, right? Because it's we can't have some sort of like negative standard deviation. And so that means that we can divide everything by it, and dividing by a positive number is the same thing, right? Like multiplying by a positive number is a monotonic transformation. So that means that maximizing this over w is the exact same thing. And now we see this is just linear regression, right? This term right here, this is just the loss term for linear regression, and we're maximizing this with respect to w. So we see that if we assume like a maximum likelihood estimation, we assume sort of a generative process, and then we're like, how can we maximize the likelihood? Then we get the same result as linear regression, which is sort of another different intuition for what linear regression is doing. So now we're going to change our generative model a little bit and explore another correspondence, in particular between regularization, which I covered in an earlier video, and putting a prior on w. So what if we consider a slightly changed generative model, and now the story of our data generation is first we pick some w, and the w comes from this multivariate normal distribution centered around 0 with covariance matrix identity times the inverse of lambda. So now we get a w from that distribution, and then we use that w for our actual generation in the data process. So now we want to find what is the best w here, considering all this information that we have. So no, we don't really just want to do the same thing here. We can't just find some w that satisfies our previous likelihood function the best, because this would just ignore the prior if we just picked the thing that satisfied the likelihood the best. So instead, we're going to use a more Bayesian approach, and we're going to basically take our prior, incorporate the data, and get a posterior from it. So Bayes' rule says probability of w given y, x, and b, so we're using conditional Bayes' rule here, is equal to probability of y given w, x, and b, so that's the likelihood function again, times probability of w given x and b. And this actually is just probability of w. This is just the prior probability. We can just drop the x and b being conditional because w doesn't depend on that. And then we've got this thing on the bottom, probability of y given x and b. And we know the top two things because we said the likelihood in the MLE, and we know what the prior is, but we're going to have a little bit of trouble with the denominator, but we actually won't need to calculate this, and I'll explain why that is. So what we just did was called maximum likelihood estimation. Now we're doing something called maximum a posteriori estimation. So it's similar to MLE, but basically we're going to calculate our posterior, and then we're going to find the w that is the mode of the posterior. In other words, we're going to find the w that has the maximum value in the posterior PDF, which makes sense because our posterior represents our views for what w is, and so we're going to pick the w that is the most likely according to that posterior. So in this case, we actually don't really need to know what the exact value of the function is. All we need to know is which w gives us the greatest value of the function. So applying monotonic transformations to our data again is perfectly fine because we only need a function where if we maximize that, find the w that maximizes that, then that will also be the w that maximizes our posterior. So this term on the bottom here has no dependence on w, so we can just multiply by probability of y given x and b, or we just drop the normalization constant, right? And that's a monotonic transformation. So if we just maximize the resulting function, dropping the normalization, then that'll get us the w that we want. In other words, we write this proportionality here, and maximizing these two things is the same thing as maximizing this fraction over w. So now we're going to take the log, right? We have two things multiplied together. We don't really want to deal with them. We're going to take the log. The log of the products is the sum of the logs. So we get these two terms going to these two terms. And then another way to explain if the normalization constant argument didn't make as much sense to you here is let's just take the log of this function here. Well, the two things on the top, in the numerator go to here and here. And then the denominator is not actually dependent on w, so we just add another term, and we add, it would be like minus log of p of y given x and b, right? And that's not dependent on w, so that's just going to be some constant. And in the end, we're going to want to maximize this over w, so we're really not going to care about the constants anymore. It's just like how when you take a derivative, right, you just you're going to drop the constants if you're using that derivative to maximize things. So that's another way to explain why that denominator doesn't really matter. But anyway, so the likelihood, as we did in the MLE, will come out to this, and then some other constant term, which I've just I'm going to just combine the constant terms at the end. And then here, for P of W, I've just put the prior on, or I've put the PDF of the prior, and now then applying log rules again, that comes out to some constant not dependent on W, and lambda over 2 WTW. And so we can plug all that stuff back in, and combine all the constant terms, and then this goes here, and this goes here, and recall again, we only care about terms dependent on W, right? That's the theme throughout. So because we're maximizing with respect to W, so we just get rid of this constant. In other words, that's like a monotonic transformation, and so maximizing this right here is the same thing as maximizing the log of the posterior. And then we're just going to go ahead and we're going to divide by beta the whole equation, and since beta is some positive quantity, as we talked about earlier in this video, that's also a monotonic transformation, so maximizing this is the same as maximizing this, which is the same thing as maximizing that, which is the same thing as maximizing just the posterior, which is exactly what we're looking for. So now, where have we seen this before? Well, this is actually exactly ridge regression. The second term here is just the loss from like a regression, and this first term right here is the regularization term, right? WTW is just W1 squared plus W2 squared all the way up to WD. And so we see that putting a prior on our sort of our generative model and imposing a regularization term are the same thing, which actually is not so surprising, because imposing a regularization term says we want our coefficients to be near zero. And imposing a prior up here just says that we think W is going to be normally distributed around zero, so it's mostly going to be around zero, and it's going to be less likely to be much larger. So we're actually doing the same thing here. We can see a correspondence between like lambda too. If we increase lambda a lot in this multivariate normal, then it's going to become much tighter, and it's going to have much more density around zero and close to zero. So W will likely end up being much closer to zero. And similarly, when we do ridge regression and we increase the lambda drastically, this will also lead us to get sort of like a flat line, to get coefficients near zero. So we see that these are actually really highly related concepts. So since we've done ridge, we're going to try and do lasso too. And I think this is a good opportunity to try and do it on your own, because the lasso regression is actually pretty similar to the ridge regression. So the hint I'll give you is that you should assume that the prior on W is that it's distributed as Laplace lambda. And go ahead and look up the PDF for that and see if you can do it. Pause the video and we'll come back in a sec. Okay, so we're going to go ahead and go through this together. So again, we're going to take the log of the posterior, right? There's some constant term from the denominator, and then we have the likelihood, log of likelihood, and then the log of the prior. Again, the log of likelihood contributes to our constant term, and then also just gives us this term right here. And then then here we have the prior on W right below, and I've just substituted in the PDF for Laplace. And then here, this term just goes into our constant, and then this term just becomes that. And so now, again, we divide by beta, right? So that, because that's a monotonic transformation, so maximizing that is over W is still the same thing. And then we actually see that we end up exactly with lasso regression. The second term here, there's regularization. And the first term here is the overall loss. So the big idea here is that priors really are like very, very interrelated, the same thing as regularization. And if you change around your prior, you change around sort of the type of regularization that it corresponds to. So sort of a cool parallel between those two frameworks.